Properties of elements and their trends in groups and periods. Okay, now we will discuss about properties of elements and their trends in groups and in periods. So now we are discussing about properties of elements and their trends in groups and in periods. So we will discuss about the valency. Okay, this we will discuss about this valency. So what is the meaning of valency? Valency valency of an element was defined as the combining power of an element with respect to hydrogen or oxygen or indirectly any other element to the hydrogen and oxygen. Okay, so see here, valency is nothing but the combining capacity of an element with the atom of another element. For example, sodium is there. Sodium atomic number 11. So its configuration 1s2, 2s2, 2p6, 3s1. So 1s2 means first shell 2 electrons will come. Okay, 2s2, 2p6 means next shell 8 electrons will come. Okay, 3s1 means last shell 1 electron will come. So the last shell is which shell? We can call that shell as a valence shell. Last shell is called as valency shell. In last shell, how many electrons are there? That are called as valency electrons. So, do you know about octet rule? Octet rule is nothing but I think already you discussed in you learn about that octet rule in 9th class. Okay, octet rule is nothing but in last shell, if 8 electrons are there, then it will stable. Last shell, how many electrons are there? We can call last shell is called as valence shell. So we can distribute the electrons in the shells, no, like K, L, M, N. Okay, so last shell, you know the distribution of electrons in the shells. Okay, so in that shell, which is last shell, that shell is called as valence shell. In that last shell, how many electrons are there? That are called as valency electron. So here octet rule means if in the last shell 8 electrons are there, then the atom of an element is stable. If 8 electrons are not there, then that is unstable. Okay, so octet rule is nothing but if in the last shell 8 electrons are there, then it is stable. Okay, so if 8 electrons are not there, then atom of some elements are some electrons are giving to another element. If more than 8 is there, then what happen? If it is giving some electrons to another elements, if less than 8 are there, sometimes it is taking the electrons from another elements, like that it is choosing. Okay, so sodium atomic number is 11. Its electronic configuration 1s2, 2s2, 2p6, 3s1. So here in sodium last shell 1 electron is there, 3s1 means in the sodium 1s2, 2s2, 2p6, 3s1. No, 1s2 means in first shell 2 electrons will come. 2s2, 2p6 means second shell 2s2, 2p6, 8 electrons will come. Next 3s1 means third shell 1 electron will come. So in the last shell 1 electron is there. Okay, 8 electrons not there, so it is not stable. So for sodium, it is easy to lose the 1 electron, or it is easy to gain the 7 electrons. It is easy to lose the 1 electron. Okay, so that's why the sodium is losing 1 electron. Okay, so that is losing 1 electron, no? Then that is called as its valency. Okay, how many electrons it is losing or how many electrons it is gaining, that number is called as valency. So sodium last shell 1 electron is there, so it is easy to lose the 1 electron to sodium when we compare with taking of 7 electron. So that's why sodium is losing 1 electron, so its valency is 1. So if the sodium losing 1 electron, in last shell how many electrons are there? 8 electrons will be there. Means what is that last shell? Second shell 2s2, 2p6. Okay, so losing 1 electron, that is its valency. Means sodium is losing 1 electron. No, how many electrons are losing, or how many electrons are taking to get octet, to get 8 electrons. That concept is called as valency. Here sodium is losing 1 electron to become stable, means to get 8 electrons in the last shell. So that's why the valency of sodium is 1. So for example, one atom of sodium chemically combined with one atom of hydrogen to give sodium hydrogen NaH. Therefore, the valency of sodium is 1. Okay, the valency of sodium is 1. One more example to understand this valency. What is the atomic number of calcium? Calcium atomic number how much? 20. Okay, configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So last shell, which shell? 4s shell. In that how many electrons are there? 2 electrons are there. It is stable or not stable? Why? Because 8 electrons are not there. So it is easy to lose 2 electrons, or it is easy to gain 6 electrons. It is easy to lose 2 electrons. That's why this calcium lose 2 electrons. When the calcium lose 2 electrons in last shell, how many electrons will come? 3s2 3p6 means 8 electrons will come. So now calcium is stable or not? So here the calcium is losing the 2 electrons. No, its valency is 2. This is the valency. Valency is nothing but to get octet, atom of the element sometimes losing the electrons or gaining the electron. This concept is called as valency. Okay. In general, the valency of an element with respect to hydrogen is traditional group number. So the element in a group 5 or above, its valency 8. Like that, chlorine. Chlorine atomic number is 17. Its electronic configuration 1s2, 2s2, 2p. Okay, I will say 1s2, 2s2, 2p6, 3s2, 3p5. Okay, last shell, which is third shell. In that how many electrons are there? 3s2, 3p5. 7 electrons are there. So it is octet? No, it is not stable. 8 electrons not there. In last shell, how many electrons are there? 7 electrons are there. So to chlorine, it is easy to lose 7 electrons, or it is easy to gain 1 electron. It is easy to gain 1 electron. So that's so chlorine is taking 1 electron. No? So we can call that we can call the valency of chlorine is 1. Okay, like that. In general, each period start with valency 1 for first group elements, increases up to 4 with respect to the group number, and then decreases from 4 to 3 to 2 to 1 to 0 in the following groups. It is applicable for any main group elements, that is S and P black elements. Okay, means first group elements its valency is 1, second group elements its valency is 2. Okay, next third group elements its valency 3, like that. It is increasing. After that, what happened? Valency of an element. Actually, the valency of an element showing its group number. For example, hydrogen atomic number 1. Its electronic configuration 1s1. S1 coming. Okay. Next, lithium atomic number 3. Its electronic configuration 1s2, 2s1. S1 coming. Means S1 like this coming. No. So here its valency also 1 or not. Already we discussed in activity 2. The valency of first group elements is 1. So means that belongs to first group element. Okay. So the valency of element showing its group number. Okay. Second group elements are there. Its valency is 2. Means it is second group element. Okay. Third group elements are there. Its valency is 3. Means it belongs to third group. Like that it is showing. Okay. Next, fourth group elements are there. Its valency is 4. So it belongs to fourth group. Okay, like that it is showing. So if the group number of the element is 5 or more than 5, to calculate its valency, we should subtract that the group number from 8. Okay, 8 minus 8. Then we will get the valency. Okay. So in general, each period starts with valency 1 for first group elements, increases up to 4 with respect to the group number, and then decreases from 4 to 3 and 3 to 2 and 2 to 1 and 1 to 0 in the following groups. Okay, so this is applicable only for main groups elements, that is SP black elements. Okay, so find out the try to write the valency of first 20 elements. How does the valency vary in period on going from left to right? Okay, so how does the valency in a period vary on going from left to right? It does not follow the regular trend. When move from left to right in a period, first it increases and then decreases and finally zero for inert gases. So if we go from left to right in a period, first it is increases and then decreases, finally it is zero for inert gases. Next, how does the valency vary and go down in a group? So in a group, when we are going from top to bottom, how does the valency is vary? So the valency is constant when we move from top to bottom in a group. Okay, so the valency is constant when we move from top to bottom in a group, because the number of valency electrons are same for same group elements. Okay, when we move from top to bottom in a group, the valency is same, it is not changing. Okay, already we discussed this. Now we will discuss one more periodic property, atomic radius. So what is the meaning of atomic radius? Now we will discuss. This atomic radius of an element may be defined as the distance from the center of the nucleus of an atom to its outermost shell. So this atomic radius of an element is nothing but it is defined as the distance from the center of the nucleus of the atom to its outermost shell. So atomic radius is nothing but it is the distance from the center of the nucleus of atom to its outermost shell. Okay. Atomic radius of an element is not possible to measure in its isolated state. This is because it is not possible to determine the location of the electron that surround the nucleus. Okay. So atomic radius of an element, it is not possible to measure in its isolated state. This is because it is not possible to determine the location of the electron that surrounds the nucleus. Why? Because it is not possible to separate the atom of an element to identify the atomic radius. So how can we measure the atomic radius? However, we can measure the distance between the nucleus of the adjacent atoms in a solid. Okay, how we can measure the distance between the nucleus of adjacent atom in a solid. From this, we can estimate the size of the atom by assigning half of the distance to the radius of each atom. So atomic radius is nothing but it is the distance from the center of the nucleus of an atom to its outermost shell. But atomic radius of an element is not possible to measure in its isolated state. Means it is not easy to separate the atom of an element, and by that we cannot measure the atomic radius correctly. Okay, this is because it is not possible to determine the location of the electrons around the nucleus. But how can we measure the atomic radius? We can measure the atomic radius between the nucleus of a adjacent atoms in a solid. However, we can measure the distance between the nucleus of a adjacent atoms in a solid. From this, we can estimate the size of the atom by assigning the half of the distance of the radius of each atom. So this method best suited to elements such as metal that can exist in a solid state. So first, measure the distance between the nucleus of adjacent atoms in a solid. From this, we can estimate the size of the atom by assigning half of this distance to the radius of each atom. Means side by side two atoms will be there, no? Measure the distance between the nucleus of the two atoms, and that value divide by 2, then we will get the atomic radius of that atom. Okay, so this method is best suited to elements such as metals that can exist in the solid state. This method is suited for the elements for metals which exist in solid state. More than 75% of the elements are metals, and their atomic radii of that metals are called as metallic radii. Okay, so more than 75% of elements are metals. The atomic radii of that metals are called as metallic radii. Another way of estimating the size of an atom is to measure the distance between the two atoms in a covalent molecule. Okay. So another way of estimating the size of the atom is to measure the distance between the two atoms in covalent molecules. Okay. So the size of a chlorine atom is estimated by measuring the length of the covalent bond between the two chlorine atoms. Okay. So this Cl2 molecule that is formed by covalent bond between the two chlorine atom, calculate the internuclear distance. Okay. So this radius is called as covalent radius. Okay. So see here, another way of estimating the size of an atom is to measure the distance between the two atoms in a covalent molecules. Okay. So for this, the size of the chlorine atom is estimated by measuring the length of the covalent bond between the two chlorine atoms in Cl2 molecule. So half of the distance is taken as atomic radius, which is called as the covalent radius of the chlorine atom. This atomic radius is measured in picometer. Okay, this atomic radius is measured in picometer. Discuss about variation of atomic radii in group. Atomic radii increases from top to bottom in a group of the periodic table. So vertical columns are called as groups. Okay, in this group from top to bottom atomic radii is increases. Okay, why? Because as we go down in a group, the atomic number of the element increases. Therefore, to accommodate more number of electrons, more shells are required. As a result, the distance between the nucleus and the outer shell of atom is increases as we go down in a group, in spite of increasing in nuclear change. So in group, when we are going from top to bottom, atomic radii is increases. Why? Because first group, once you take hydrogen, atomic number 1. So its electronic configuration 1s1, means it will come in first shell. Okay. In first group, one more element, what is that? Lithium, its atomic number 3, electronic configuration 1s2, 2s1, means 2 shells required. Okay. Next, sodium, atomic number 3, electronic configuration 1s2, 2s2, 2p6, 3s1, means it requires first shell, second shell, third shell. Okay. So hydrogen, it requires only 1 shell. Lithium, it requires 2 shells. Okay, means hydrogen, it requires 1 shell, that is K shell. Lithium, it requires 2 shells, that is K shell and L shell. Okay. Next to sodium, atomic number 11, its electronic configuration 1s2, 2s2, 2p6, 3s1, means first shell, second shell, third shell, 3 shells it requires. Potassium, atomic number 19, its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, means it requires 4 shells. Hydrogen required only 1 shell, lithium required only 2 shells, sodium required 3 shells, potassium required 4 shells. So here atomic radius is nothing but the distance from the center of the nucleus to outermost shell. So in hydrogen, once you take, it requires one shell. No? Measure the distance between nucleus to 1 shell. Okay. Next, lithium, it requires 2 shells. No? Measure the distance between center of the nucleus to second shell, last shell. Increasing or not? Increasing. Okay. Sodium is there. Measure, it requires 3 shells. Okay. 1, 2, 3. Okay. So measure the distance between center of the nucleus to last shell. Increasing distance or not? Increasing. Potassium, it requires 4 shells. So measure the distance between center of the nucleus to last shell. It is increasing or not? Increasing. Okay. So in group, as we move from top to bottom, when we move from top to bottom, atomic radii is increasing. Yes or no? The distance from the nucleus to last shell, increasing or not? Increasing. Okay. Understood? So in group, when we are moving from top to bottom, atomic radii is increasing. Why? Because here when we are going from top to bottom in a group, atomic number is increasing. To accommodate it require more shells. Shell number also increasing. Then the distance between the center of the nucleus to last shell is increasing. That's why atomic radii also increasing. Atomic radii is nothing but the distance between the center of the nucleus to last shell. Okay, the distance between the center of the nucleus to last shell is called as atomic radius. Okay, so here one table is there, no, group 1 and group 17 elements given, its atomic radii values given. Lithium 152, sodium 186, potassium 231, rubidium 244 and cesium 262. So these are the atomic radius values in picometers in for group 1, and group 17 also given once you see. Discuss about variation of atomic radii.